Okay, and so in order to get to build the one-line accumulation function, instead of having the many-line accumulation function, which will be way too long when we have very small intervals, first thing we said was, okay, let's just forget about that piecewise accumulation function. How would we write an expression that would calculate, say, the accumulation at 5? Okay, so do you remember how we did that? So how did we write the accumulation in other words, the y coordinate of this point is the total accumulation so far of the height of the rocket based on these constant rates, right? Based on this approximate rate function. How did we do that? Remember?
We did all the completed intervals, then we added the current interval.
Okay, so what about the completed intervals, right? So completed intervals are like things, and a value is going to be a computation of numbers. So what was it about the completed intervals, Yazra, that we did?
We did the change in y of every interval.
Okay, good, right. So we summed up the changes in height. So we get a change in height from each interval, and then the accumulation is like the running total of that, right? As time's going by, we keep doing like the running total, the sum of all the accumulation so far. So what did that look like? Somebody knew. What does it look like to do a running total of all the accumulation so far based on these constant rates? And my great goal is to get us done by 1 o'clock today to give you some time back. But that's a little bit going to depend on you guys when I ask a question, if we can jump in quick and keep it moving. So what was what was the way that we wrote an expression to get this accumulation?
We did like RH of, and then your first interval, so like RH of 0.9, and then times 0.9 plus RH of 1.8 times 0.9.
And what in each one of these, what is that doing, Ashley? What's each?
The change in t, like the distance between them, is always 0.9.
Okay. And so this what does this little calculation then represent?
It represents the accumulated height for that interval.
Yeah, good, right. So it's a little change in height, right? For that interval, for this one it'd be this interval, right? So there's a change in height associated with this interval at this rate, whatever r sub h of 1.8 is. And that gives us that change of height. So I think that's this amount right here. That right there. Okay, and then we kept going. And then what happened at the end? So we're doing r of 5. Somebody knew. So what happened then? So something a little bit different happened at the end. Do you remember what that was?
I think the interval's shorter.
Okay.
So it wouldn't be multiplied by 0.9.
All right, so tell me. So this is 4.5 here. So tell me what happened in the last little bit of height change.
Is it RH of 4.5 multiplied by 0.5?
Yeah, that's it. So we had all the accumulated bits of height from what we call completed intervals, and then we had a little bit more height for what we call the height in the current interval, right? So the current value of x is, if the current value of time is 5, then we're partly through an interval, and we're going to have a little bit more height according to how far we've gone into the interval. And what is that 0.5? How do we represent that symbolically?
Change in time?
How far we've gone. Okay, but can you be more specific about the notation? How far we've gone in the current interval?
Yeah, is it x minus 4.5?
Okay, but we have a really important symbol for that. How far we've gone in the current interval. Remember? Anybody?
The dx?
Yeah, dt. Yep, dt, exactly. So actually, these are what. So we haven't really talked about it yet, but the interval width that we pick before we even start this, or that's going to be our delta t. That's a moment, right? A moment is our delta t, and then so delta t is 0.9, and then dt in every current interval, dt varies in the interval, right? It starts at what value? dt goes from what to what in this interval? dt.
4.5 to 5.
Okay, he wants 4.5 to 5. Agree with that? Is that what dt does? Here we said dt was 0.5. So does dt...
Does it vary from 0 to 0.5?
0 to 0.5? Okay, what varies from 4.5 to 5? But actually, in the whole interval, right? So not 5 is just, we're going to just pause time. If I'm talking about this particular interval, then something varies from 4.5, but not to 5 in the interval to what? What is that?
5.4.
Yeah, so from 4.5, what varies from 4.5 to 5.4? Is it dt? What's varying in this current interval from 4.5 to 5.4?
The time?
Yeah, that's just t, right? That's just the value of t, right? So what does dt vary from? From what to what? Someone said it before.
0 to 0.9?
Right. The beginning of the interval, your dt is 0, and then when you get to the end of the interval, it's the value of delta t. Makes sense? And so then here we are at 5, and when we're at 5, t equals 5, dt is 0.5. Okay, so this is the idea. Okay, so let me give you the pretty version here. Okay. All right, so we said so get this change at t equals 5, we have all the change from the completed intervals and then the change in the current interval. And so this is what we did. We said we took our r sub h at the beginning of every interval times the change in time in that interval. Right? So I think Ashley was talking about this one, right? Okay, and then we have a little bit more change in the current interval, which is at the current rate, is only for a change of 0.5. Okay, so our accumulation function, so this is going to be like a of 5. A of 5 is going to be this, all this, plus that. Where's the plus right here? Okay, so do you see how that's A of 5, right? We get the sum of all the changes in height from the completed intervals, plus a little more change from the current interval. Does that make sense? So that's not that hard, right? That's not a difficult thing, because all we're doing is doing m dx plus m dx plus m dx to get an accumulated dy, right? And we're just summing up the m dx's. Okay, so this one line accumulation function that I'm talking about is it's kind of complicated. There's lots of details. There's lots of functions involved. But when it all boils down, this is exactly what it does. This is what it does, and so you got to keep this in mind. That what it does, what it's doing, is not a hard thing, right? It's just summing up m dx plus m dx plus m dx for all the completed intervals, plus an m dx for the current interval. Okay, so keep in mind that we're going to start putting the nuts and bolts and the machinery together here, and it's going to start getting a little like, whoa, this is getting a little complicated, right? That's okay. just keep in mind that when it boils down to this. Every value of the a function is gonna be calculated just like this. Okay, so here we go. Let's look at, I've got this, any questions before we move on? So we're doing the one-line accumulation function. And this is all part of this problem that we're doing. You know how fast a quantity is changing at every moment. You have the rate of change function. You want to know how much of it you have at every moment. And that's our accumulation function. Okay? So that's the big picture here. So let's bust up this. And we're going to go try this. See how this is working. This is very slow for me earlier. But actually, I showed you guys this, this file at the beginning of the semester just to talk about what variables, constants, and parameters. And it's still awful. Okay, so I'll just try to do it manually here and see if I can keep it smooth. No, it doesn't go smooth. So the animation used to run smoothly and really fast and really nice, and it's a shame that it doesn't anymore. So just imagine this thing running smoothly. Ugh, yuck. So I'm just gonna, it'll just be slow. Okay, it'll just be super slow. Okay, so what we want to do here is want to identify. We got lots of things. Double question marks are like entities, functions, have like a written description, and then single question marks represent actual values, but we're representing with symbols. Okay, so these are actual numbers that we're representing with symbols, the single question marks, and then double question marks represent like things, entities that you would put a phrase on, right? But they're not values. Okay, so let's talk about the red. What would the red graph represent? What is the red graph? So in the context of what we've been talking about here.
G of x, just the function.
Okay, but yeah, it's a function, and I'm calling it g, but what is that g function? In the context of what we've been working on. You know how fast a quantity is changing at every moment. You want to know how much you have at every moment.
It as the rate function.
Yeah, that's the exact rate function, right? Okay, and then somewhere, my files are not, I thought this was ready here. Yeah, so that really, yeah, let's pause this here. Maybe this is it? No? Shoot, maybe this is it? Yeah, this is it. Where's my approximate rate function? It's gone. Everything's turned on. Maybe there's another slider up here that I missed here. View. View. There we go. Okay. All right, so very good. So then what about the double black question marks? Which is representing this. Wow, that's going even slower than before. So I gotta do this here. It'll just be super chunky and not smooth, but it'll go faster at least. Yeah. All right, so what about the double question marks? The double question marks are referring to these black horizontal lines that are being formed. as x increases. What's that?
The approximate rate of change function.
Yeah, that's the approximate rate function, right? So this is our step function, like we're using the left, right? Left side of every interval. This is the approximate rate function. Okay, next. So, and then we see, what is this question mark down here? Kind of gives it away somewhere else in the animation. What is that right there? Represented by this arrow, starting from the y-axis all the way out.
X.
Yeah, this is the current value of x, right? Current value of x is that one. What is, so I don't know if we've talked about this yet, but we're actually starting accumulating from some non-zero value, and we call that a, so x equals a. So a, lowercase a, we use to mean the x value where we're going to kind of start this accumulation process, if not zero, okay? What do these, so now I think I want to turn something that off, but too late. Okay, so what do how about these double question marks for the purple? What could that be talking about? So from here to here, and it's not a function or a value. So what could that be talking about from here to the start of the current interval? What do we call those?
The completed interval?
Yeah, completed intervals, right? So this are completed intervals. And what about the yellow double?
Current interval.
That's the current interval, right? Current interval is the gold double. So I think we got all the double question marks. We got the exact rate of change function. We've got this emerging approximate rate function. We got our completed intervals, which is this purple, and then the gold is the current interval. Okay, what's the blue? So now I'll do the single question marks. What's the blue? What's the blue single question mark? So we just talked about this.
Dx.
That's dx, right? It's how much variation in the current interval, right? How much variation you have in the current interval. So that's our dx. Very good. So what is this representing then? This kind of fixed value from here to here. And that could be here. This could also be from here to here, or here to here, or here to here. It doesn't have to be that one, but that's just the one I'm showing.
Is it delta x?
That's the delta x, right? Delta x is our width of our intervals. And the blue one is dx. The variable, do you remember dx was a variable? Delta x was a parameter. And so that's the variable amount of change in the current interval. Okay? Then we have one more thing here. So let's turn all these on here. So now, turn. So there is. There's dx, completed intervals, current interval. Okay, left x, we'll talk about that in a second. What else? I think that's everything. Yep, so we got our exact rate function. I'm calling that r sub f. Approximate rate r. There's the completed intervals. Current interval. Okay, here's our dx. Oh, there's delta x. Get turned on. Delta x. Okay, and so then we have this value called left x. Left x is a function. It takes the current value of x and gives back the starting value of x for the current interval. So no matter what x value you get in the current interval, that function will return or give the starting value of x. So notice how it stays constant, right? It's staying constant as long as x is in the current interval. But then when x goes to the next interval, then left x jumps and becomes the start of that interval, okay? So you remember doing this on the first day of class in terms of variables and parameters? So now we have the meanings of this. This is about what we're going to be using the rate function to build an approximate rate with delta x intervals, and then that constant approximate rate is generated in the current interval as far as dx, right? Using the rate at the beginning of the interval. Okay, so let's just pause this here. Say right here. That looks good. So here I have my A is 0.5. And delta x is 1.5. And the current value of x is, it looks like, is it 10? Okay, so I want you, given, we want to find, given this is our exact rate function, we want to write an expression that calculates the approximate accumulation at 10. So I'm going to start a new GC file here. Okay, and so given this setup here, I'll define this function. So let's just copy and paste. So copy the rate function. I'm going to call it, this time I'm going to call it r sub f of x equals, paste. Okay, so there's my r sub f of x. And so now I want to write an expression that calculates a of 5, but it doesn't really. So Control T. A of, I'll just make text here. A of 5, because we don't have that defined in GC, so I'll just do it that way. A of 5 equals what? So I'm going to write an expression now using what we've been learning. Oh, so A of 10, sorry. Let's actually make it a little bit faster. Let's go back a little bit here. Can I get 4? Sure, 6.33. Okay, so let's do A. That'll be a little faster. Let's do A of 6.33. So help me out. You guys are going to do this. So what will I type in my GC file here to calculate A of 6.33? Based on this approximate rate that's built from this exact rate with starting from 0.5 with delta x of 1.5 and at x equals 6.33. So what should I type in to get that amount of accumulation?
Um, 1.5 times r sub f of 2.
Can I do r sub f of 2 first? Is that okay?
I believe so.
R sub f of what? What do you want to do?
2.
2? Okay.
Times 1.5.
All right. Is that part of the deal here? You like it? So what else? Is that it? Is that A of 6.33?
So I'm going to buddy in.
I'm gonna take over for Richard. So you all agree that that's part of it. So,
Yeah, and then plus R of F of 3.5.
RF of 3.5, okay.
And then times 1.5.
Okay. What else?
Can we do RF of? Can you use any value within the range for the x, as long as it's within the interval?
This is R sub f. So you tell me. This is the exact rate function. I'm using the exact rate. I didn't define an approximate rate function. I'm using the exact rate function. So what's the answer to your question?
No.
No, it's okay. No, that's you're thinking about the approximate rate function, and that's great. So
RF of 5
RF, okay, of 5
times 1.5.
Okay, how are we doing? Angel, you agree with all this?
Wait, would it be 1.33?
Why 1.33?
Because it's going up to 6.33.
So is this the current interval? Donna, you agreeing with that? You changing your mind?
I agree.
Oh, you're nodding. Okay, so just make sure. All right, is this it? Is this the accumulation starting from 0.5 out to 6.33? So the total accumulation to 6.33?
I have a general question.
Yeah.
I'm not sure where we're getting like 2 and 3.5 and 5.
Okay. So what are we just can you tell me what we're doing in general? When we do the rate times 1.5 and a rate times 1.5?
Yeah. So wouldn't it, since you said like change in x is like 1.5,
Mhm.
so oh, okay, never mind. Okay, I see it now.
You see it now?
Okay.
Okay.
Yeah. Oh, my bad.
Okay, so is this correct? Is this A of 6.33?
I think we're
According to-
missing an interval.
Tell me, Donna.
I agree.
I think it's RF of 0.5 at the beginning times 1.5. Or you can just add to the end.
Yeah, so this should be, if we were, perfect, it'd be at the beginning, but it's not going to change the value. So you want R sub f of what?
0.5
Okay.
times 1.5.
How about this? So we have what? All the accumulation from completed intervals, and there's 3 of them. 1, 2, 3 completed intervals, plus a little more, almost a whole completed interval, but just not quite. That's the accumulation due to the current interval. Okay, how about doing this in a handheld calculator? What do you prefer? Getting this number? Handheld calculator or GC? You see what you have to do in a handheld calculator to do this? It'd be pretty awful, right? There'd be a lot of punching. You'd probably make a mistake at least once on your way to the answer. So this is the power of function notation and GC, right? So hopefully some things like this, when you're trying to compute values, things like this really make GC a huge advantage, right? You can define the rate function, and then you can use function notation to represent the values. You know exactly what they mean without ever having to go through and calculate this awful number, right? And you can set up expressions. You can copy, paste, edit. So just a plug for GC, right? So to get students to let go of the security blanket of a handheld because they're so used to it, when something like GC can do something a lot more efficient, a lot more powerful, both for just computing answers and as a teaching tool, right? Okay, questions on this? So that's the same thing we did with the rocket basketball. And then once again, this is going to be the structure of the one-line accumulation function that we're going to start to build now. Just never lose sight that it's just the rate at the left times the whole interval, plus the rate at the left times the width of the interval, the rate at the left times the width of the interval, which is just a bunch of little dy's. Dy's from the completed intervals, and one last dy from the current interval. That's what this one-line accumulation function is going to do for us. Okay, so any questions on the animation that we were using, identifying everything, right? There's lots of parts and pieces here. So we got to have all the language down and understand what everything is. There's lots going on. So any questions on the animation or calculation?
I have a question on the calculation.
Sure thing.
So is this like, when we say we were doing a direct calculation, is this like an approximate value of the accumulation function at 6.33?
Okay, let me throw that back to the rest of you. Is this value approximate or exact, and why?
Isn't it approximate since we're using approximate rates to find it?
He says it's approximate because we're using approximate rates. So we're assuming these constant rates in every interval.
Yeah.
And that's our approximate rate function. Does that answer, Richard?
Yeah. So I'm going to guess I might be just speaking too far ahead, but we're going to make a lot of smaller intervals to get more accurate.
That's why we need the one-line accumulation function and not the piecewise. Because to get an accurate, version of the accumulation function, we're going to need lots of really small intervals. And then super small. But if we have the one-line accumulation function, making the intervals smaller doesn't change anything. It doesn't make for more work. It can take care of that. It's built into that one-line accumulation function is you can choose any size interval that you want. Okay? Cool. All right. So other questions? Here we go. So let's do it. So now we're going to embark. So you know how fast the quantity's quantity's value is changing at every moment. You want to know how much of the quantity you have at every moment. Okay. So here's a snapshot of what we just worked on. Right. We got A, the current value of x, the current interval. We got our delta x intervals, dx, approximate rate function, exact rate function, everything. Okay. So now let's talk about at 6.75. At x equals 6.75. So I need to move this now. I'm not going to be able to see your faces anymore because I gotta. All right, actually, I can try it down here and see if this works. There we go. Okay. Oh, now it's at the bottom. Jeez. I'm struggling with my. Maybe on this side. Let's try this side. Oh my gosh, this is awful. All right, forget it. Sorry, I'm not going to be able to see your faces. This is just not cooperating. Okay, so same thing with, so 6.75 is the current value of x here, right? 6.75 right here. And so we know we're going to have an m dx, m dx, m dx for 3 completed intervals, plus a little bit more for the current interval, right? So what is the value of r? What's the r of what for the first interval? R of what? Based on the way we have this set up. We need this rate, which is the rate of change at what x value? So we're talking about
something. I don't remember the value.
No.
Is it A?
A. Well, all exact values now. All exact. So it's A.
Got it.
Okay. And then times delta x. And so now the second interval. Second interval. What's going to be the x value for the start of the second interval?
A plus delta x.
Right. Does everyone see that? And then the third interval. Start of the third interval, the x value will be? Someone knew?
A delta x.
Oh, you broke up there. Sorry. Say it again.
A plus 2 delta x.
That's right. Now notice, we're starting at the start of the third interval means adding how many delta x's?
1 less than the third interval.
So to get to the start of the third interval, we go across 2 intervals. All right, what about the last rate? The last rate is going to be, or the x value for the last interval? Come on, guys. Anybody?
A plus 3 delta x.
Thank you. And notice, this is for the fourth, this is the rate in the fourth interval, or the current interval, but it's the fourth interval. And how many delta x's does it take to get to the fourth interval?
3 delta
3.
x's.
How many delta x's does it take to get to the third interval?
2.
2. How many delta x's does it take to get to the beginning of the second interval?
1.
1. Right? So if we want to generalize that, right? We know that, right? So in the first interval, right? What happened? We had a plus 0 delta x. In the second interval, a plus 1 delta x to get to the start of the second interval. To get to the start of the third interval, it was a plus 2 delta x. So it's going to be, let's see here. Just don't know how this. So what's the x value for the rate in the jth completed interval? What would the x value? These are the x values. These are the x values. What's the x value for the start of the jth interval? So one more time. The start of the fourth interval, what's the x value for the start of the fourth interval? A plus 3 delta x. The start of the third interval, the x value at the start of the third interval is a plus 2 delta x.
2 delta.
So what about the jth interval? What's the x value? What are we going to put into R to get the x value for the rate of the jth interval?
A plus
A plus B plus 1.
A plus,
Angel, I'll let you take it.
Sorry, J minus 1.
A plus j minus 1. Is that the x value of the jth interval? That's not it.
Yes.
You got the hard part of it, but you didn't, it's not right.
It's j minus 1 times delta x.
Yeah, j minus 1 delta x's, right? J minus 1 delta x's, right? So you go across j minus 1 intervals to get to the left side of the jth interval, right? And so we need j minus 1 delta x a plus, okay? And what's the a value for the rate in the current interval? If there's j completed intervals, then what would be the x value for the rate of the current interval? So it's going to be the same pattern. How many, if there's j total completed intervals, now we want to go to the current interval. How many intervals do we go across to get to the current interval?
Is it just J?
Yeah, j, right? All of them, right? So you're going to go across all the completed intervals, and then you're going to start the current interval. So there's j of them, j completed. So j times delta x gets you to the start of the current interval. Is this making sense so far? Okay, so now we want to express erase some junk here. So now we want to express what is what's the x value in the 101st interval? Okay? So imagine that x is in the 101st interval rather than the 4th interval. We want to express a of 6.75. What will that look like? What will that look like to express a of 6.75 if rather than being in the 4th interval, here it is in the 4th interval, that x value of 6.75 is in the 101st interval? What will this thing look like? So just even if you don't know the final answer of to this question, tell me something. Tell me something if x is no longer in the 4th interval but the 101st. Then how will it change the situation? So this is 101st interval now. Is there just one thing we can say that's different about this now? If rather than the 4th interval, we're in interval 101, right? So the delta x is much smaller, and we get to the 100. So 6.75 x equals 6.75. It's no longer in the 4th interval, but the 101st interval. So how will this be different then? Will there still be 3 things we're adding here plus this one?
We're going to be adding a total of 101 things.
You're going to be adding a total of 101 things. Okay? So break that up. So be more specific. What are the 101 things we're going to add up?
Can I use ellipses so it'd be like r of a times delta x plus r of a, or r of a plus delta x times delta x plus dot 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 plus r of a plus 100x, 100 delta x times delta x, and then the last one would be plus r of a of 101.
So it'll be a 101 right here? This will be 101? No,
I agree.
No, this is the 101st interval. This is the 101st interval.
Interval, but yeah, the left side is the 100. So
how many completed intervals will we have?
100.
100, right? So rather than having 3 things here added together, we'll have 100 of these added together. And then what will how many delta x's do we have to go across to get to the left side of the current interval? What will this number be?
100.
100 or 101? Because Richard said 101. No, Angel, you're saying 100.
I agree with the 100.
No, back to 100. Okay, we're going to change your mind. Okay, good. All right, so we're 100, right? So how can we make, so rather than write out 100 of these, plus 101, plus another one, how can I do that? They all kind of look the same. So how can I write out summing up 100 things that look the same? And get it to fit down here.
It's the summation notation.
Yeah, so this is summation notation. It's meant to help us, not to scare us, right? So it's like a good thing, not a scary thing. And so we're summing up a bunch of what? R of somethings times delta x. And what did we say for the j'th interval? What goes in here for the j'th interval? What's the x value for the left side of the j'th interval? Anybody?
A plus minus 1 times delta x.
Right. We already worked that out, right? It's always a plus 1 less delta x's than the interval that you want. a plus j minus 1 delta x. And then j is going to start at what and go to what?
Start at 1 and at 101.
Start at 1 and end at 101? Are we going to be able to include the current interval with this?
No, so it would be 100.
100. Yeah, we can do that for the completed intervals, but what's the problem? Why can't we put the current interval in here? What's the problem?
It's like not being multiplied like the full delta x.
Right,
Like,
because all of these in the sum are multiplied by a full delta x. Completed intervals are full delta x. The last interval will not be. It'll be multiplied by dx, right? So we can't include that with the sum. So then what do we do?
just slap it on.
Yeah, just slap it on, right? Slap it on. Add what? R of. Now what will the, and we'll have times dx. What will the x coordinate of the left side of the current interval be?
A plus j dx. I mean, delta x.
Yeah, right. Good. So we're going to go across all the completed all j completed intervals to get to the left side of the current interval. But then that rate will be multiplied by dx only, not delta x. Okay, so this is kind of our accumulation, one-line accumulation function is kind of taking form here. The sum of all the accumulation from completed intervals plus a little more accumulation from the current interval. Okay, any questions? Did you follow all that, right? So we first had to generalize what the x value at the start of the jth completed interval. Oh, this isn't right. So this is not j. J is changing, right? So we don't want to put j there. What do I want to put there instead of j? I don't want to put there. It's not j. We know what that value is. What is it? So j stands for, it changes. It's first it's 1, and then it's 2, and then it's 3, and then we add all them up for every value of j from 1 to 100. We don't want j here. What do we want here?
Would it be 100 as well?
100. That's right. Because we're gonna jump over all the 100 completed intervals, and then that puts us at the left side of the 101st interval, right? That's always one less, right? So across 100 intervals puts at the left side of our current interval, which is the 101st interval. Yeah, so that should be 100. Okay, so questions. So I mean, we still got work to do, but we're getting closer. Anybody have a question?
Yes, sir.
Okay, so what happens next is as x changes, right, as x increases, the number of completed intervals changes, right? Because as x is going to vary through completed intervals. So this is the number of completed intervals. And this itself is a function of x, right? Because you saw it in the animation. As x increases, every time it makes it through an interval and starts a new interval, well, you just added one more completed interval, right? Every time it moves to a new current interval, you added one more completed interval. So number of completed intervals depends on x. So when you say express a of 6.75 and you know that it's in the 101st interval, well, this is easy because you know there's 100 completed intervals. But if you want to try to write a of x, well, different values of x result in different numbers of completed intervals. So we got to figure out what the number of completed intervals is given any value of x. And then this right here, this is what did we name this in the animation? Do you remember? This is the start of the current interval. We had a function for that. Remember what that was?
Was it left of x?
Yeah, that was left of x, right? Left of x was the x value at the start of the current interval. So this a plus 100 delta x is actually left of 6.75. Should write that. Left of 6.75 is the same as a plus 100 delta x. It's the left x value of the current interval. Okay. Any questions? Okay, so so here's the deal. So it didn't make it as far as I want so that you can start on the next GC project is like a big one. All that ones so far have been worth 20. This one's worth 50. So let me just show it to you. And I think you can kind of no, I think you need this to start that. But let me show you what it is. So last chance before I erase. Any questions?